Hello everyone, and welcome to today's webinar about the ISP tuning. I'm here with Claudio. Welcome, Claudio.
Hi, thank you.
We got also Cathy online. Hello, Cathy.
Hi.
Just for your information, the webinar is going to be recorded. So if you want to rewatch it later, you can. You also will be able to ask your question in the chat along the way, and we will answer them at the end. So what's on the agenda for today? First, a quick reminder about what is ISP tuning. Then the main part of today's webinar is going to be a demo of a tuning process step by step. Then some advanced fine-tuning and enhancements beyond the basic tuning. And Cathy is going to be presenting a tuning example. So let me just... So a quick word about our products and services here at DXOMARK. We got a variety of testing tools, which with a combination of hardware and software solutions to create a tailored lab that suits your need for image quality evaluation. Based on these testing tools, we have a wide range of services to help you in any phase of production, from R&D to the final implementation of your camera module. We also got in-depth data, with our Insight program to better understand the consumer preferences, and overall we can achieve any custom development to your specific need. A quick word about Camera Analyzer, which is our modular IQ Live solution, which has been improved and updated for more than 20 years now to adapt for the latest imaging technologies. You can use it to run measurements with anything with a camera, basically, from any industries, from mirrorless camera and automotive to 3D camera and AR, VR. Both for photos and videos, and to get detailed reports. These measurements are repeatable and can be automatized. We can also provide everything from the charts and the lights to the IQ software to perform the analysis. You can learn more about them on our catalog, and we will detail in a bit which elements are we going to use today for the demo. So Claudio, can you tell us what is the ISP tuning?
Yes, first of all, a point of language, of terminology. In the business, when we say ISP tuning, in actual fact, we are probably talking about the tuning of our image pipeline, of our imaging system. And this, of course, part of that happens on our ISP, which is an image signal processor, so a component designed specifically for that purpose. But oftentimes there are other parts of the pipeline that are executed, that run on other computational units that are on my system on chip, which can be more general. For instance, there could be a digital signal processor, which is also related to signals, but is more generic. It could also process audio at the same time, for instance. Or you could have a part of your pipeline that relies on the graphical processor, so the GPU, the very same that you use for the rendering on display. Or even it could be a completely general purpose processing unit, such as your CPU, what we call normally your processor, which could be multi-core, for instance, or something dedicated to neural networks and AI, so what's usually called an NPU, neural processing unit. All of these at different moments may be involved in your pipeline. For instance, we say ISP tuning, but we also set the 3A the auto exposure, auto white balance, and autofocus, which typically does not run on ISP, it runs on CPU.
So why my algorithm would run on one of these processor and not the other?
A general rule of actually hardware design, electronics, let's say, is that the more a component is specialized for a task, the more efficient it is at performing it. So the ISP that is designed just for the specific purpose of processing images is very fast and very effective at doing it. However, at the same time, it's hard-coded. It's more difficult to change its behavior. It's less programmable, if you will. It's less general purpose. When you increase the level of abstraction, you get something that is more and more potentially adaptable and powerful, but the less and less effective. So everything in the scale has at least some degree of variation. Even the ISP, where let's say the algorithm is predefined, you have some parameters of that algorithm that you can choose, and that's also part of the tuning.
So how do we do that?
Well, as engineers doing the tuning, we have a certain number of steps that we are going to take. The very first thing is the bring up of your imaging system. So you start with something with the default setting for everything. The image is not even looking like an image. The first thing you need to do is bring up your pipeline so that you get an image that looks like an image. And then you want to get an image that looks like the scene. So your next target is what we call fidelity. So accuracy with respect to the ground truth. Once you get there, then there is a wide range of possibilities depending on what's the application for your image. You are going to optimize your image quality attributes depending on what is the specific purpose of why you're taking the image. Maybe you are doing an automotive camera, needs to detect pedestrians crossing the road, then maybe you need to be sure that certain contrasts are handled properly. Or maybe you're doing a surveillance camera, they are often black and white. In that case, color is certainly not a priority, but maybe sharpness is, and so on and so forth.
So you're talking about a pipeline,
yes.
Right? So can you tell us a bit more about that?
Yes, a pipeline is a very diverse set of possibilities in real life. So first of all, we need to understand that the term pipeline, it's a metaphor, it's an analogy. There is no actual linear sequence of blocks one after the other, like the one I depict here in the picture. It's a logical pipeline. Realistically, this is a certain number of functions that are implemented in different computational units of my system on chip, and that I'm going to call in a certain order to achieve a certain result. The next thing is that here I put an example. It's an example of a very simple pipeline. In this scheme here, I have neglected to represent everything that happens before the capture, including, more importantly, the 3A, so the auto white balance, auto exposure, and autofocus, but all the blocks that are between the moment of the capture and the moment of the setting on file, let's call it, the output. When I say all the blocks, it's all the blocks that I've chosen for this example. In actual fact, there is no hard rule about what blocks you're going to find on your pipeline. Your specific pipeline could have more blocks than that, or fewer blocks, or the same in a different order. They could be the same but with a different name, or maybe two of these, the operation is performed in a single unit, or something that I represent here with a single block could be split on two different blocks in your pipeline. It's very diverse. So keep in mind, this is just an example to fix the ideas, to have a general impression of what a pipeline looks like without any pretension of exhaustivity. There are, anyway, a certain number of commonalities that we can identify, specifically the fact that there are several color spaces that are going to be used in your pipeline. When you take the image from the sensor, it's not even an image yet, it's a raw file. A raw file is a matrix of values in which every value, every photosite is represented with just one number. So there is only one channel for each photosite. that depends on the specific color of the Bayer filter that is in front of your sensor. This is typically represented with a higher depth, a higher number of bits than the final image is going to be. And this is the closest you can be to the physical reality of your sensor and lens. For this reason, some corrections are very nicely applied at this stage, because everything we do after that tends to be destructive, so you cannot recover the information. This is the moment when you have maximum information. At the same time, these are specific to the particular colors of your biofilter and a higher number of bits per sample. So maybe the algorithm needs to be it's a bit heavier. So you're not going to be able to do everything in RAW for a variety of reasons. So at one point, you are going to move to an RGB space. So when I say RGB, obviously the RAW is more often than not also an RGB in the sense that the Bayer filter has a red, a blue, and a green channel. But these are red, green, and blue in some sense. It happens to be the red, green, and blue of whatever the spectrum of your filters on Bayer are. Whereas the RGB space is some kind of standardized RGB space. So for instance, sRGB. And you have 3 samples, 3 channels per sample. So every pixel actually has a color. It has the 3 components, red, green, and blue. And another wide variety of algorithms are run in this space. This is standardized, which means that third-party algorithms are common, that you can buy off the shelf. And certain corrections are more logically applied in this space. And then typically, before you go to the final saving of the image, let's say, before you get to the JPEG encoding, for instance, there is another conversion of color space, which typically what it does, it dissociates the luma channel that represents the lightness of the scene. So let's say the black and white correspondent of your image, your grayscale image, to a chromatic component on 2 different channels. There are several reasons to do this. File compression is anyway going to do that. JPEG anyway does that. Why? Because we know that when we look at an image, our sensitivity to the degradation on the luma component are not the same as the one on the chroma component. So when you compress a file, when you reduce its size, and you're going to lose some image quality in doing that, well, you can focus your allocation of resources on things that are more sensible. So typically in a JPEG, you have a lot more bitrate that is allocated to the luma component than the chroma component. But for the same reason, some algorithms of your pipeline can prefer to run at this stage where you have separated the notion of luma that goes with the notion of exposure, the notion of chroma that goes with the notion of color, because conceptually we might want to work in this space more easily.
So what do we need to achieve this ISP tuning, and what are we going to use today for our demo?
So as I mentioned, the first thing we need to do is we have to get an image that looks like an image, but then we need to get an image that looks like the scene. So we need the scene. So we need the target charts at the very least. So I'm going to use very simple charts in this presentation because I designed a very simple pipeline, and this allows us to understand more easily what might happen on a pipeline like that. So one chart that I'm going to use is this one. And at the center, many will recognize a very common color checker. This is pretty standard, which we encased in this particular frame here, which has other measurable elements that we have introduced at DXOMARK. The idea being that it's always better if you can minimize the time you spend shooting in the lab. So if you can take more measures on the same chart, that's better. Another objective chart that I'm going to use is the dot chart, which is also pretty standard. And finally, we have this one here, which is a bit more particular. It's something we designed here at DXOMARK, and it's our perceptual target chart. As you can see, this is not something that is printed. These are actually physical elements in 3 dimensions. And we have, so to speak, a little bit of everything. We have some uniform parts and some more detailed parts, and we have faces, and we have text, contrast and color, and so on and so forth. The idea being that I need some kind of guidance to tell me how to proceed in my tuning. So what I'm going to do is that I'm using this chart for perceptual validation. I'm going to look at this image and I'm going to analyze it and decide what is the biggest problem of my image right now. And once I have this piece of information, I can go to one of my objective charts, take an objective measurement, and use that for informing my tuning choices.
So that's our charts. How are we gonna light up these charts?
It is very important when you do your image quality testing that you light your scene in a precise and repeatable way, so precise and accurate way. There are two main axes that you have to control. One is what's called the illuminance, which is the amount of light that hits a surface, specifically the chart, and it's measured in lux. And the other one is the spectrum of the light that is hitting the chart. So obviously the spectrum is a function, not a number, but usually we express the color of the light using the colorated color temperature, that it's a temperature, it's measured in Kelvin, and it's the temperature an object should have to glow of that color. There are plenty of possibilities. We are using our multispectral lighting system, and the particularity of this system is that it doesn't have just a discrete number of different type of tubes and bulbs that you can turn on and off. What it has a variety of LEDs, each with a certain class of spectra, and then with our software, we combine the different spectra of the different LEDs to get basically whatever spectrum you want in the span of those LEDs. So we can tune very accurately what spectrum we want to put on the scene, and clearly we can also reproduce the so-called standard illuminance. For instance, of course, when you do a tuning, you have to do a variety of conditions, but to fix our ideas and to keep it reasonably manageable in a presentation, we're going to do our examples in one lighting condition. The spectrum we have chosen is the tungsten, which is a black body emitting at 2700 Kelvin. And as a lux level, we put 20 lux, which is a low light condition. We chose this because it's a bit more interesting in our tuning, because it's a bit more challenging than other conditions.
So we set up everything, our lights, our charts, our IQ software, and our camera module. We take the first picture, and that's what we get.
Yes, this is a result that is possible if you just take the default settings that come predefined with your tuning. And that's what I meant when I said the first thing you need to do is have an image that looks like an image, because now it doesn't look like anything, right? So what's the most striking problem with this picture for you?
It's quite dark, isn't it?
It's quite dark. You can't really see anything. And of course, photography means writing with light. So the first thing we need to worry about is getting the amount of light. More specifically is the lightness. The lightness is the apparent quantity of light in the picture. Why do I say apparent? Because there are two factors that influence the lightness of an image. One is the actual amount of light you got with your sensor, but the other one is by what kind of conversion I make light into digital numbers. So specifically the gain that I apply to this conversion. The total amount of light depends, generally speaking, on two factors, which are the aperture of your lens and the exposure time. But usually on embedded systems, the aperture is fixed. Okay, they're not DSLRs. So we basically have the exposure time that we can choose. And then once you have decided a certain exposure time, the other one is the gain or sensitivity or ISO speed. These are not exactly equivalent, but they all mean the same general notion of by how much I multiply my light to get a number. So first of all, I need a target for my lightness. So I need to know how much lightness I have right now. Target exposure is generally the average level of lightness in the scene. To get a notion of that, what we can do is that we take our color checker, we select a patch of known reflectance that is going to fall somewhere in the middle of the dynamic of my sensor. So I take the patch with reflectance 18%, should be represented with in the center of the dynamic of your sensor. And we measure the value, the colorimetric value of that patch in the standardized LAB space, in which the L stands for lightness. This lightness should fall in a correctly exposed image somewhere between 40 and 60. Ideally, we would like 50 everywhere maybe, but this is not always going to be possible because, yes, I can control my exposure, I can change my exposure time, I can change my sensitivity, but there are side effects. So when I increase my exposure time, I expose my sensor longer to get more light, I always incur the possibility of motion blur. As soon as something moves in the scene, or if I move with respect to it, for instance, by shaking, well, this is going to appear blurry around the objects. So there is a limit to the longest exposure time that I can afford. That depends on a number of factors, including how big your sensor is, what is your focal length, so because it influences the field of view and so forth. But generally speaking, for your camera, you're going to have an exposure time that you are going to say, okay, I cannot do longer than that because otherwise I get motion blur. And once you get there, you need to start increasing the gain, the ISO speed. And increasing the ISO speed, you're getting the same amount of light. You're just multiplying it by a bigger number. So yes, the average increases, but so does the noise. So sometimes you might want to not get an image that is between 40 and 60, because if you do that, then you clearly have too much noise that you cannot manage. So you have a trade-off and you renounce some of the exposure in favor of a clearer image.
That's the compromise right there.
Correct.
So we measure that, we apply a correction.
Yes, and let's say that in this case, my sensor, and my other parameters, the focal length and so forth, are such that I can do a satisfactory tuning. So now it looks something like this.
So now we get to see a bit better. Mm-hmm. We can also see that the perspective isn't right?
It's not exactly the perspective. What you're seeing here is geometric distortion. Geometric distortion depends on the geometry of the lens. It's an optical property of the lens, and it's particularly visible for devices, for lenses that have a short focal length, so basically a large field of view. And you have lines that are straight and parallel in the scene, not straight and parallel in the image. The good news is we know how to measure this. So the dot chart, this is the purpose it was originally designed for. The reticle of dots in the chart is fixed, and the distance between consecutive dots horizontally and vertical is also fixed, which means that when I look at the image and they are not at the same distance, I can trace this distance along the field to get a quantified information about the distortion. So it's because the phenomenon is most often radial, what I'm going to do is I'm going to average for every distance from the center, and I get a profile curve like the one that we see in figure. Sometimes we are very, very lucky, and our pipeline wants as an input for correcting distortion exactly the kind of output that the analyzer measurements gives you, which is a set of coefficients for the polynomial that describe these curves. In other cases, you're pressed to do a bit of trial and error because you know the amount of distortion, but maybe your pipeline has a few controls and you're not very sure what they exactly do. So you have to play a bit around, and this curve is satisfactory for you.
Is that something we need to do for different illuminance?
Not necessarily, because distortion is a purely optical property. Whether there is much or little light, the lens is always going to distort the same way. So for convenience, we only measure one condition. And generally speaking, when you can do whatever you want, you do what's easy, not what's difficult. So the best thing to do is you put yourself in the lowest sensitivity, a lot of light, bright light conditions, a very neutral light like a D65. You take the picture there in the best possible condition for the measurements, so you have a very accurate measurements, and then you are relatively confident that you can apply it to all other lighting conditions without worry.
So in our demo, we are still going to do it at 20 lux.
Yeah.
We applied the correction.
Yes.
And now our lines are more straight.
Yes, but you may also notice that the border of the image has disappeared a bit.
Yeah.
We needed to crop. Why? Because in the original image, the object had been warped to not be straight anymore, but it was still an image, which means that the borders were straight. When we warped the image to compensate for that, now the objects are squared, but the border would appear distorted in the opposite direction. So because we need an image that is rectangular, we crop that part out.
So no, maybe can we address this green hue, right?
Yes, it's very green. But the reason is we said we start with a sensor that gives me a raw file with its own definition of what's red, what's green, and what's blue. And in the end, I want to work in an RGB space. You need to tell your pipeline how to do that. So there are two operations that you need to perform. These are the compensation of the white balance scales, and the other is the color rendering. The white balance is basically the fact that if an object is of neutral color, if an object is gray in the scene, it should appear gray in the image as well. And the color rendering is the fact that the colors should look like themselves. The red should look red and the green should look green and so forth. So for the color scales, it basically depends on the relative sensitivity of the different channels. But when I say that the object is gray and it looks gray in the image, notice that the camera does not see a gray object because the color of the light. In tungsten, the color of a tungsten light, it's like a light bulb, it looks yellowish, orangish. So this light is going to reflect on my gray surface because gray is uniform, plus the yellow is going to look yellowish, which means that the difficulty here is not to decide what to do when there is a yellow light on a gray patch, is to know what's the actual color of the light. And that's what the 3A algorithm is doing, is collecting information to tell me, well, actually, now it's a yellow light plus a gray object. And for each different illuminant, I am going to provide different white balances scale, so to compensate for this and always get a gray object. The color rendering, it's a whole matrix. Why is it a matrix? It's a 3x3 matrix. You have an RGB input and an RGB output. The RGB input is the sensor RGB, the actual color, the actual values in the raw file that represent the filters of my sensor, whereas the output RGB is the standardized RGB, for instance, sRGB. And I have a system of linear equation to move from one to the other, and this is represented with a matrix. This also goes with the white balance and therefore goes with the color of the illuminant, temperature of the illuminant.
So we do both of them, right?
Yes.
And then
when we applied our white balance and our color matrices correctly, which, by the way, it's most often you just take the output from analyzer and you can put either exactly these values or sometimes the inverse of these values, depending on your pipeline. But generally speaking, whatever you have on your pipeline is quite close to the analyzer output for it.
Okay. So now we have corrected the colors and the white balance. What I see there is a lot of noise, right?
Yes, especially in some parts where the signal is a bit uniform, you're immediately going to see an appearance of gray, basically. And it's also quite colored. There are several reasons for it. First of all, there is the inherent noisiness of the capture. So 20 lux is not very much light, so you have some noise from the capture itself. And then we applied an ISO speed, we applied a gain, we multiplied the noise the first time. Then we also applied the white balance scales, which means that two of the channels have been multiplied by something larger than one, and on these two channels you even more increase the noise. So in the end, without denoising, the image is not really exploitable. I say without denoising because we haven't tuned anything yet, but the pipeline you have surely has at least one denoising block, and most likely more than one working in different ways in different parts of your pipeline. So first thing we need to do is to quantify how much noise do I actually have in here.
So we take our
yes.
checker chart with the gray frame.
Yes, right? In this case, it's the gray frame in particular that we're going to use. Of course, these are also uniform patches, but they're quite small. When you are taking statistical analysis, you might want something a little bit bigger, so you have more information. And this is why we have these uniform patches here all around that cover a certain variety, a certain range of gray levels. And the notion of noise is actually, intuitively, we can say it's variation where there shouldn't be any. So the patches themselves, they are flat and gray, they're uniform in color, but I look at the image and I see a variation. So mathematically, we quantify variation with something like variance or standard deviation. Instead of looking at how much noise you have, because then it depends on whether I'm looking on a dark patch or a bright patch, engineers that do image quality often discuss in terms of signal to noise ratio. So this is the curve that I'm plotting on this page. And this particularly is done in a logarithmic scale called decibel or dBs, because that correlates more strongly with human perception. What is a good value of noise? Well, 0. We all want to have 0 noise, but that's almost never possible. So what is an acceptable level of noisiness? Well, when the signal to noise ratio is less than 20, your image isn't very good at all. So you want to be at least over 20. Ideally, over 30, it starts not being noticeable anymore, and everything over 40 is actually quite good, actually very good. So depending on how much light you have in the scene and what is your ISO speed, you're not going to make the same choice because denoising has its side effect. So as I said, my pipeline is a single exposure pipeline. I'm not merging images together. There is no temporal denoising, for instance, because it's a very simple pipeline. So how is going to do the denoising? It's going to mix pixels together. Neighboring pixels are going to be mixed together, which makes the image blurry. And the stronger I do my denoising, the blurrier I get the image. So there is some kind of compromise that I need to find between exposure, noise, and blurriness of the final image. And at different light levels, I'm not going to get the same results. That's why I chose the 20 lux. It's a more challenging condition. Let's say I get something acceptable with my sensor.
We applied denoising, right?
It's a lot better. You notice that it's not completely flat. There is still noise, okay? But the appearance of noise is compatible with what we would have with an analog print, for instance. And if you look at the big image, you don't actually notice it anymore. So we are, at least for the moment, satisfied with this result.
It's acceptable, right?
It's acceptable.
But now we've also lose a bit of sharpness, right?
Yes, and which probably we didn't have much to begin with, because such a simple pipeline, it's typically accompanied with cheap hardware. So probably my lens may be plastic or anyway not very sharp, certainly not a DSLR. So it wasn't very sharp to begin with, and then I denoised it, and now it's very blurry. So what I need to do is to use my sharpening block. There's almost always a sharpening block. The sharpening block usually comes after the denoising block, at least after a denoising block. Because sharpening a noisy image is not a very good idea, because sharpening is a filter, it's a spatial filter applied that increases the difference between neighboring pixels, basically. And if I do this on noise, I'm going to create structures of noise, which, first of all, are problematic themselves. And if I do a denoising after that, because the denoising algorithm is assuming some kind of statistical behavior for noise, in my sharpening, I have perturbed the statistical properties, and the denoising doesn't work anymore. So you always do sharpening after the strongest denoising. How do we measure sharpness? Well, have you noticed that in these uniform patches here around, these are not parallel to the borders of the chart. They are slanted. Slanted edges are the way to measure sharpness. And particularly by we use the standardized metric of sharpness, which is the modulation transfer function, the MTF. Of course, the MTF, it's not a number, it's a curve. So we might want a scalar, a single number to associate this curve. People who do optical design, they're just working with the blurriness that is due to the lens, usually just take one value of the MTF, like MTF 50, and go with it, because physical properties are constrained, and so tracking one value in a certain point of the curve tells you a lot, actually, of what's doing everywhere else. But when you do sharpening, that's no longer the case, because you're applying an algorithm. So you can change this curve with your algorithm however you want. How do I get a single number from that? I need to take into account the whole function, the whole MTF. But I want to weight it. Specifically, I want to weight it in a way that makes sense with my perceptual impression of sharpness. How do I do that? There is a notion called acutance, in which the MTF is weighted with something called the contrast sensitivity function, which is the gray, lighter gray area that you see in the MTF graph. And that represents how sensible is the human eye to that specific spatial frequency in certain viewing condition that you have to choose for your analysis. So you multiply the two together, you do the integral, and it gives you a number that you can very roughly consider like something like a percentage of sharpness. This also tells us that when I do my sharpening, one could think naively that, well, I want my MTF to be 1 everywhere. It wouldn't really matter, because as you can see, the very high frequencies, they are very low as weight in my average, so I don't really need to do that. The low medium frequencies have a stronger importance. So when you see a sharpened MTF, you're often going to see something that goes over 100% between 0 and 0.25, and then it goes rapidly down, and maybe it's very, very low after 0.3 or 0.4. Yeah.
Okay, so we apply some sharpening, then it's much later.
Clearly, it's not the sharpest image I've ever seen. You don't have all the fine details, but certainly is acceptable.
Yeah. So now the next thing I can notice is in the corners, we have some strange color leaks.
Yes, what's happening here, it's called lateral chromatic aberration. Remember when we corrected our distortion, we said, oh, I measure the distortion, like if it was a single value, a single thing. In actual fact, you have 3 channels, red, green, and blue, on your sensor. And because of how light works and diffraction of the lens, the 3 might each have a slightly different pattern of distortion, or in our example, not so slightly, which results in the fact that your image looks fine in the center, but as you go in the corners, the 3 channels, red, green, and blue, tend to not be in sync with each other anymore. And here in the very corner, you can basically see, well, the green is where the red is and when the blue is, with these colored halos around the object. So correcting it comes to measuring the distortion per channel. Now, it depends on how your pipeline works, and that's why there are also different color spaces. Maybe you have 3 channels of distortion, and your pipeline wants a red polynomial of distortion, a green one, and a blue one, or it reasons in terms of distortion in the luma channel, and then it has a separate block for lateral chromatic aberration that only requires the deviation from the luma of the 2 channels. The analyzer measurement gives you the results in the 2 forms, and you are going to use whichever is convenient for your pipeline.
So we applied the correction, that's the before and the after.
And you see that now the channels are again in sync, so the image doesn't have this border, at least at this scale. Maybe if you zoom very, very, very much in, are going to have still this effect of half a pixel, let's say. But for the moment, we are satisfied at this scale, we don't see this degradation anymore.
So if we still look at the corners, we can see that it's darker than compared to the center.
Yes, and this is why it's very important that your lighting is uniform, because you have to be sure that in the scene this wasn't the case. Okay, my target chart is of a uniform gray all around, and when I set it for testing, I also measure the center and the corner with the light meter to be sure that they're the same level. So why is it darker in the corner than it is in the center? Well, this is a problem that has a lot of names, actually. We can call it vignetting or luminance shading, sometimes roll-off, fall-off, but they basically all mean the same thing. Because of the geometry of the lens, some elements are projecting a shadow over others, and you get less light in the corner than you get in the center. This is something that we can actually measure. So the simple way is you have a uniform surface, you light it uniformly, and then you follow how the gray level evolves in the field from the center to the corner, and the gray level is going to go down. Doesn't even need to be perfectly uniform. In fact, we can do it with a dot chart. We just don't look at the black dots, we just follow how the white evolves in the field. And we can, again, we average radially, because this phenomenon is typically radial, because it's a lens phenomenon. And we get our amount that goes from 100% in the center to maybe 20% in the corner. What we need to do to correct that is that we multiply by the reciprocal of this number. It would bring it up to the level that it was in the center. Now, I said before, optical phenomena do not depend on the amount of light in the scene. That's also true for vignetting. The vignetting is always the same whether you're 1,000 lux or 1 lux. However, the effect of the correction is not. Because the effect of the correction is what? I'm multiplying some pixels by a bigger number. Is like if I were increasing the sensitivity, the gain, the ISO speed in those parts of the image, which means more noise. So if I am 1,000 lux and I don't have much noise to begin with, I can correct a lot and it's still fine even in the corners. But if I am at 20 lux, maybe I'd rather leave a bit of vignetting in the corner rather than have a strong noise in the corner. So it's always a compromise, I trade off.
So we found a compromise here in our situation.
And it's better. The vignetting is almost completely gone, but the noise in the corners is not that much worse than the one in the center. So it's fine for the moment.
A good trade-off. But we can more clearly see in the corners a color cast.
Yes.
Right?
Yes. This is particularly noticeable if you see at the canvas of our target chart, which is of a uniform straw-like color. And it looks pretty realistic in the center, but it's pretty greenish in the corner. Why does this happen? Well, again, we said we corrected the vignetting as if it was only one, but you have 3 channels, and maybe your device is doing 3 slightly different things on the 3 channels. In this case, it depends typically from the presence of an infrared filter, which tend to be quite directional. So in the center, when it's hit directly, it might work with a certain efficiency, but in the corners, when it is hit at an angle, it may let some infrared light pass that is going to be captured, for instance, by the red channel. So what happens is that different points of the sensor see a different color of light, would need a different white balance scales, but you don't do that. So what happens is that you see this color cast when you go in the field. But the same way we measure at vignetting, so by looking how much light you have in the center with respect to the corners on the dot chart, we can do channel by channel, and this will tell us the 3 roll-off per channel. And then again, depending on your pipeline, maybe you have 3 different curves you put in for red, green, and blue, or you have one block that corrects vignetting, so the Luma channel, and another one that corrects CLS, colored lens shading, in another block, maybe also in another color space.
Okay, so we apply for each channel, right? And then
it's almost completely gone.
Yeah,
it's not totally out because, again, it's always a compromise. We don't want to overdo it, but it's not visible at this scale, so we are satisfied.
So we've achieved several improvements.
Yes.
Are we done yet?
Well, that depends on what we want to do. If I look at that image and I look at the actual chart, in fact, if I measured it with instrumentation like a radio spectrometer, it would tell me that this is very close to reality. Question I have to ask myself, is reality my target? Depending on the application, I might have, for instance, security application, surveillance, things like that, where I would want to increase the detectability of certain elements, or I might have other purposes in mind, medical, or so. What are we going to do with this image?
Well, for today's demo, what about a nice looking image?
Simply. Sure. So maybe you have your laptop, you need to do a webinar online and you want it to look nice. So from this point of view, if I take the image that I have so far, the image is accurate, let's say, that represents with fidelity what's happening in the scene, it is a nice. Why is not nice in the opinion of the user?
Well, it appears a bit flat, right?
Yes. So the layperson term flat usually translates in incorrect or unsatisfactory choice in the contrast of the image. Notice that the contrast you see on the screen is, in fact, the real contrast that you have in the scene, but we don't like it. Why? There are two reasons. The first one is because you're not looking at it in the same condition. I'm here and I'm looking at the object, but there is everything around it, so my brain is doing a certain processing of it, and I get a certain perception. When I look on it on a screen, it's not the same thing, and so the same exact contrast is not going to perceive the same way. Plus, there is the fact that maybe I want to enhance reality a bit. So, first thing, let's measure what the contrasts are. I take my chart again. I have plenty of gray patches of non-reflectance. So what I can do is that I can compute how much light is coming off each of them, because I know how much light I am sending on them and how much they reflect. And on the other end, my file tells me how much light is going to come out from my screen. I plot one against the other, and in my fidelity example, it's going to be pretty much a straight line, because there is a linear proportionality relationship between light in the scene and light on display. Okay, but what we actually want, if our target is enhancement of the perceived contrast, is to boost the contrast in the dark part a little bit, and to reduce the contrast in the brightest part a little bit to avoid the saturation phenomena, for instance, in the sky. So you're going to shoot for kind of an S-curve, like the one that it's presented there.
We apply this S-curve to our image. We take the image, and then much better.
It's already better. Clearly, I have a very simple pipeline, okay? So I just globally apply the variation of every contrast in the same way. If you have a more evolved pipeline, maybe you have a block called local term mapping that is going to be able to make different choices of different curves in different parts of the image depending on the surrounding to increase also the perception of dynamic. But in our simple example, we can get something like this and be pretty satisfied with it.
So now if I look my image and I look our DXOMARK chart, it's pretty similar, but it's still a bit dull, isn't it?
Yes. Especially after the correction of the contrast, it appears not to have enough color. Although it's accurate, because of the same phenomena of what's happening around it in the scene with respect to when I look at it on a screen, it looks like a bit missing color. So the notion that the image quality attribute we're talking about is called saturation. So colors have a certain saturation that basically tell us how close they are to a pure hue of that tint. How green is my green? How red is my red? We have our color checker. We know very precisely what is the color, what is the full spectrum of each one of these patches. And so we can plot on a color space of our choice the ground truth and the measured point, the one that I see in my screen. And I can have an arrow that points from the real color to the one that appears on the screen. Well, if I want to boost saturation to make the image look nicer, what I want is that the arrows point outwards. So basically they are in the direction of the borders of my gamut, so the pure colors. This, again, is a simple solution that it's purely by playing around with the matrices that I was showing before for the color rendering, advanced pipelines, maybe quite smarter than that. They can actually sometimes detect what the object is and for instance say, oh, this is the sky, therefore it is blue, and I want a very deep blue, so it looks very nice, and they are called memory colors. So things that people know the color of, even if they are not seeing the scene. But in my example, I will just play around with my color matrix until I get the amount of a couple of JNDs, a couple of just noticeable difference from the original color to get a bit more, yeah, a little boost to the colorfulness of the image.
And we applied it in our case globally.
Correct.
So that's without, before, and after.
Yeah. So we get something that it's clearly more colorful. Your user might like it or not. This kind of choice, it's really depending on the final user.
Yeah. So it's nicer to look, but how can I know it's nicer for everyone? Is it depending on the use case, right?
It depends on the use case. It also depends on the user, because there isn't going to be something that everyone likes. So you need to know your final user. This is why, for instance, at DXOMARK, we have our insights. Okay, these are panels in which we go in different places in different countries, and we ask to a variety of people that between two choices, which one they prefer. And you are going to get different results, for instance, by country, because of cultural preferences. But for the same reason, maybe you get different results depending on age group, of gender, and so forth. Notice that some things are problematic for everyone, okay? Some problems are just problems. Distortion, I measure it, I correct it, everybody's happy, no problem there. Other things, yeah, in principle, everybody would want an image with exactly zero noise and perfectly sharp, but we cannot get that. So we have to make a choice, and different people may prefer one choice over another. One person might say, oh, I don't mind a bit of noise, but I want it very crisp, very sharp, whereas another one would say, oh, okay, it's a bit blurry, but at least there is no noise. So in that case, you need some kind of guidance, some intent, as they say. Other things are not even a compromise, are just a choice. You see that when I choose the color for my image, I didn't really worry about what's going to happen, because I can always choose a matrix. The only thing is the colors are going to be different. There is no side effect other than the colors themselves. In that case, it's an actual choice. So some people might like one, some people might like another, and you need to know your final user very well to know which one they prefer.
So in our case, in today's demo, we've tested in one luminance condition and one color temperature condition. Is there any other challenge?
Well, in fact, the point is that at the very least, your pipeline has to have triggers, which means situations for different settings based on the amount of light in the scene and the color of the light of the scene. This is the very basic, but often they have more. So maybe, let's say that you are doing astrophotography, you're tuning a telescope of some kind. These are devices that have a great variety of operational situation in terms of temperature. They are they are on a satellite in the cold of space. They're very, very cold, and then they work for a couple of hours, and the electronics themselves warm them up. So the temperature of the sensor changes, and when you change the temperature of a sensor, you change its noise patterns, its noise models. So we tuned our denoising based on how much light I have in the scene, but in that case, I would also have different settings depending on how hot is my sensor at the moment. There are other possibilities. For instance, gyroscope. Okay, many laptops nowadays are provided with a gyroscope, and when I move, they detect it. Because I'm moving, maybe they decided to do a shorter exposure time, because so they don't have motion blur. But if I have a shorter exposure time, I need to increase my gain to have the same exposure, which also increases the noise. Anyway, I've changed my exposure. Everything that is tuned based on exposure is going to change, including, for instance, vignetting correction that we have mentioned before. So there are sometimes some unpredictable or anyway unexpected interaction with the different blocks. Okay, maybe I'm doing a video conference with a colleague of mine. on my laptop, and then for some reason I have to change meeting room. I take my laptop, I stand up, I walk around with it, so I'm moving, and I have vignetting appear. This is not something that I would have expected intuitively, but because of the strong interactions among the different blocks of the pipeline, this could actually happen. And this is the reason why I always go back to my DMC chart, because every time I need to tune something, I always need to make sure that I'm not introducing some regression somewhere else because of some unpredictable interaction between tuning blocks.
So in order to make the correct change adjustments, we need to know what's in the pipeline, right?
Yeah, pretty much.
How can we know that?
Well, you might want to collect as much information as possible from the manufacturer themselves. The problem is that sometimes the manufacturer can't or won't provide much information, depending on the kind of, often depending on how much you paid for your pipeline. You might have a very nice documentation of tens of thousands of pages where everything is explained, and then you have a very convenient software where you just put in your numbers in a graphical interface and you run and you get your new tuning, and maybe even a simulator that once you give a raw image that you have extracted from your pipeline, because you try what would happen if I applied this setting, and you don't need to shoot again. That's the ideal case. On the other end of the spectrum, you get a few hundred pages of documentation where there is vaguely explained what this number does, and you have tuning like strength 1 to 4 or things like that, and you don't really have support from your manufacturer, and you need to put a number hard-coded in some C++ file and recompile everything and go back in the lab and shoot. So depending on your situation, you might count more or less on having a priori information about your pipeline. You can always do a posteriori information. Basically, you treat your pipeline like a black box. You go in your lab, you take your measurements, and you check what happens when you do a certain things. Anyway, it wouldn't be wise to rely on a completely open loop tuning. You always need to check what's happening in every part of your system. So you need to spend time in the lab and perform tests, and performing always the same test, hence the importance of having a repeatable hardware and a repeatable lighting, so you know that, well, yes, actually my noise is decreasing when I choose this new tuning setting, and my sharpness is increasing, and so on and so forth.
Well, thank you, Claudio. Now we're going to see what Katia has to say. Katia, are you there?
Okay, cool. Yeah, actually, I think what I'm going to do is not giving a tuning example, because currently we are working with some customers at our DXOMARK lab in our headquarters in Fremont. That's the next step. But I would like to give a very brief introduction from the marketing perspective, like how we help our customers with all from camera production all the way to ISP tuning, as well as like the mass production wise. So I think some of you might know about us, Leopard Imaging. We started 2008 in the heart of Silicon Valley, and we have been in the market for 17 years with our engineering expertise. And also with our manufacturing capabilities, both in the US and Southeast Asia, that we have so far worked with hundreds of thousands of well-known customers. So our business model is not just online shopping, but also like a one-stop shop from POC customization and mass production, including, as I mentioned, the ISP tuning and driver development. And one more thing is, like from last year, we worked with DXOMARK for the image quality testing lab, which we have worked on very like amazing projects. And there are like, I think over 200 engineers and executives from different big companies visited us. Next page, please, Adrian. So a very short, like a brief introduction about all kinds of cameras we have been doing. It's like automotive, as Adrian mentioned, that how DXOMARK help automotive grade cameras doing all the tests. and also robotics, tech, that's agriculture technology, automation, as well as drone aerospace that we made in the US, help a lot of Department of Defense projects. Of course, metaverse, AI edge devices, that's how we build this whole ecosystem of imaging solutions. The next page, please, Adrian. And for automotive, that before we do all the ISP tuning, we can already provide our customers the requirements they want. Either it's the long wiring distance, or the DMS and the OMS applications, and also requirements like IP67 and IP69. For all this is like we start from scratch with our customers based on the requirements. The next page, please, Adrian. Thank you. And what we focus now with DXOMARK in our US headquarters is we want to help with more robotics industry companies, because we have tons of experience in this. And DXOMARK for a long time really focused on the automotive one. But now we're kind of combining autonomous driving and let's see, agriculture technology into this autonomous agriculture technology. And besides that, for automation, that's another new field that we are working on to do not only the manufacturing part, but do more imaging testings in our US factory. So for key features that we have done a lot of projects with our partners like NVIDIA, Qualcomm, Intel, and NXP, both in the US and in Europe, to support all those projects. And Adrian, next, please. And you can check our website for a selection of stereo camera, depth camera, USB cameras with different connectivity. And we are welcome to answer any questions, just shoot us an email. And the next page. I'll just give a brief picture of how we build the whole ecosystem of agriculture technology imaging solutions with our cameras, with different resolutions, and plus the AI box we integrated into the system. Also the next one. And also the same as our ecosystem for automation solutions. And the next, please. And also, as I mentioned, we did a lot of DoD projects in our US manufacturing factories. So those are some like examples that we did with Amazon Prime Air and with our TOF cameras, as well as the stereo cameras. And IoT solutions as some examples for smart cities and like Amazon cashless card. Before we go into the DXOMARK lab part, just want to mention that from the next one, please. From the camera provider perspective, from the quality-wise and the vision-based software parts, with the DXOMARK, the imaging test lab, we could do more image quality tuning as well as ISP tuning and all the software part that we can implement into the whole system. So the next page, I want to introduce to all of you about our image quality test lab together with DXOMARK that we built last year in our Fremont headquarters. So if you go to our website, you can see all the services we provide with all the high advanced equipments all the way from DXOMARK, be it MSL room like 3D and the stereo vision bench, flare bench, or the LED flicker modules. And I know this year we're going to accept more advanced equipments to help with our customers. So as I mentioned, that we are already in some projects to provide some ISP tuning, because previously leopard imaging has done years of ISP tuning, but with DXOMARK, the new tools, and we are going to have a broader range of customers on this side. And the next one. So this is the example that what we did with our cameras on benchmarking, services. And this one has already, we're going to apply the module to more customers. So this is like a T2020 dynamic range one that we have a full report on this automotive grade camera. And with the DXOMARK lab, we have a better sense of how this camera can help our end customer. Actually, it's a big automotive customer that to provide like a better quality of the cameras, and how this can help their customers to have enjoy a better journey of the imaging solutions. And I think that's all I want to share today. And if you have any questions, just feel free to message us anytime.
Well, thanks a lot, Kathy. That was very instructive. So to quickly wrap up, what did we learn today? So we've covered the basics of what is ISP tuning.
Yes.
We've done a demo of the basic tuning to calibrate and get a usable image. And we've made some enhancement to this image for a specific use case. In our case, it was a perceptual rendering. I think we are done. Now is the part where you can ask your questions. You can write them down in the chat, and we will try to respond to them. Yeah.
Just to emphasize, this is clearly a primer. One does not become an expert in tuning of pipeline with 1 hour presentation, but I think we managed to introduce a certain number of elements that can give you an idea of what's behind the tuning, what kind of attention you need to have on different aspects, and especially the importance of having hard data, numbers, in order to drive your tuning choices. Yeah.
We have one. How can we improve camera tuning for computer vision application, such as ADAS front-facing cameras? That's another use case, right?
Yes. So there is always going to be some kind of tuning of your pipeline. But when you have a specific purpose in mind, what's happened is the image quality attributes are more or less always the same, but the relative priority are different. So your tuning is going to be different. For instance, you might not need color at all in an ADAS application, but you might want more contrast, and it doesn't need to be realistic, okay? Because you are not looking at the image to see how nice it is, you are looking it through your windshield, right? So what you want is something that enhances your human vision, and specifically I can run an algorithm to it. So maybe, for instance, in a case like that, my handling of contrast would be very different, because I don't want something where I can recognize the features of a person. I don't care who is crossing the road. I just want to know that somebody's crossing the road. I might want to boost the contrast a lot so I can easily detect shapes, for instance. My handling of sharpness versus noise might also be different, because maybe I don't need to have a very sharp image of the person, but I have to be able to detect it from the background when there's somebody dressed with dark clothes in a dark environment, and I don't want it to be completely covered with noise. So we are probably going to through the same steps we did, but you're making your choice differently because your trade-off are different, because the finality, the purpose of your image is different.
Well, thank you for your question. Another one is, up to what degree can the tuning be automated? Does DXOMARK provide any solution for this?
Very good question from my friend and colleague, Dr. Barbos. You can, in some cases, automate a part of the tuning. And we have, usually when you think of analyzer, you think of our graphical user interface because they're very convenient. You drag and drop your image and you get nice graphs and so forth. But behind that, there is also an API. There is a Python API that can run measurements. You call it from Python, and you can integrate it in your Python scripts. It's called the workflow manager. And for instance, for something like the white balance or the color rendering, well, you can take a set of pictures of your color checker, this one here, under a certain number of illuminants, and then you run a nice script that you have put all the images of the same illuminant in the same directory, and then your script goes through them and say, okay, for that illuminant, I do my calculation with Workflow Manager, and I get this matrix for white balance, this matrix for color rendering, applied it in my tuning, and so on and so forth. Similarly, you can do that for if you want to, you decide a certain thresholding of compromise between how much vignetting you correct and how much noise you get. Our noise measurement that I have done on this chart, with the Workflow Manager, you can put a uniform region of interest wherever you want. So you can do it on a gray chart. You measure on the same picture taken under different lighting conditions, so for different lux levels from 0.1, 1, and so on and so forth, up until 10,000 if you need that. And you measure how much vignetting you have and how much noise you have, and you can compute how your SNR would change if you correct it perfectly. And so you put a target on that, and you compute automatically your curve for that lighting condition, and so on and so forth. Depends on what kind of degradation you want to correct and what blocks you have available on your pipeline. But generally speaking, yes, you can integrate our measurement tool directly in your automated tuning pipeline. Yes.
Okay, thank you. Thank you for your question. For MTF, you showed different charts.
Mm-hmm.
What are the differences between MTF, SFR, and acutance?
So MTF and SFR, there are some purists at home that are not going to be happy, but they are basically the same thing. SFR means spatial frequency response. MTF means modulation transfer function. In both cases, you are going to look at the same curve, which is by spatial frequency, how much your signal is going to be amplified or attenuated by your imaging system. Acutance is slightly different because acutance is a scalar matrix that you extract from an MTF curve. So it's an integral measurement where you take your MTF curve, you give different weights to it depending on your contrast sensitivity function, and then you integrate all together. So at the end, you get a number. So it's typically easier to make decisions based on a number than it is on a full curve. So it's a good idea to use the acutance. Why would I use a different chart? Depends on a lot of factors. It depends on basically how convenient it is and how appropriate it is to measure your device in a certain way. When I say that I do my measurement on this chart, I'm implicitly assuming that I can frame this chart correctly, that I can see the edge with a sufficient number of pixels to have a good measurement, and I can light the chart uniformly. This is not necessarily true in every case, because maybe you have a very short focal length or a very long focal length or a very low resolution. Depending on the specificity of your systems, a certain chart might be more or less adequate than another. Let's say that you're doing an automotive system where the focus distance is several tens of meters. I do not have a lab that big, right? So I cannot measure it in that way. How do I do it? Well, I take our MTF collimator setup, in which being collimated, the edge appears as if at an infinite distance, and I emulate what would happen if I put the chart several tens of meters away, which I cannot actually do. In other cases, maybe I have a field of view. I have to be very, very close to the chart in order to frame it. I may want to use a very big chart. And in that case, maybe I use a wall-mounted MTF chart, and so on and so forth. It also depends on what your pipeline is going to do. If you have a purely optical system, like a DSLR taking a raw file and measure the raw file sharpness, Whether I take my edge black and white or two different gray levels, the result is going to be the same because the behavior of the system is going to be the same. But if I have something that is a bit dependent on the content because there is a complex pipeline that makes different choices depending on the context, well, low contrast like this one here or our radial MTF target chart may be more appropriate than a black and white target chart. And in fact, in many cases, if you have a complex pipeline, you wouldn't measure sharpness on a slanted edge at all. You would rather use a textured pattern like the one you find in our deadliest target chart, because in theory, on a purely optical system like a DSLR, the result I get on the one or the other is exactly the same, but it's not the case if you have a complex pipeline, and the textured pattern of the dead leaves chart, it's more representative of a real scene than it is a simple edge. And in fact, if you have a very, very evolved pipeline which uses neural networks and whatnot to detect a face and do something special with a face, well, then you need a face. So we have realistic mannequins that are the appearance of a real person, but that we control very, very finely, so to be reproductive, on which we have trained neural networks to give you a scalar value of sharpness, or more appropriately of detail level, that you can use as if it were an acutance, but it's actually on a specific type of content.
That you can repeat measurements.
Correct.
Well, thank you. I think that we've answered all the questions. Thank you, Claudio, for your time and your expertise. Thank you, Cathy. And thank you for all you for attending this webinar. You can always contact us if you need anything or if you have any question. We will be happy to respond. Stay tuned for our upcoming webinars. Next one is going to be about IEEE P2020, which is now becoming IEEE 2020.
Yes.
So stay tuned for that. Thank you and have a good day.